Hi. Uh, Thank you everybody for taking time out of the weirdness that is the world to come to my talk on the importance of phylogenomics in understanding the evolution of North American compositae. This symposium on linking phylogenetics and ecology is particularly interesting to me, having spent the last 5 years sort of working on these questions of evolution in this group and at a macroecological scale, and some of the frustrations we've had at trying to link phylogenetics to ecological data. So I'll get into that a little bit later. Been working on this with Jennifer Mandel at the University of Memphis and the Smithsonian. Just finished a postdoc there, and I'll talk a little bit about where I'm going in the future towards the end. So just as background, the North American Compositae, one of the largest flowering plant groups in North America. About 1 in 10 species is in that family. But quite what has sort of driven the diversity and rates of diversity in this group is unknown. People speculate that maybe it's the sort of herbaceous fast generation time that has allowed for adaptation rapidly and at scale to the environment. Maybe it's the seed is able to disperse large distances and sort of travel and traverse ecological niches. Secondary metabolites maybe have broken away from predator interactions or allowed other evolutionary adaptations. But the angle that we are most interested in is that maybe the tolerance to challenging environments has allowed them to exploit niches that other plants are not otherwise able to do so, and has allowed them to diversify and radiate very successfully. In order to do this and sort of any of these large scale questions, we need sort of 4 main branches of data, or at least 3 of them. Spatial data we're sort of mostly familiar with. Big databases have been around for a while, GBIF and IDIG-Bio. And data cleanliness has typically been an issue with this, but the tools for cleaning and processing these data are becoming relatively simple to use and straightforward. Environmental data is maturing very rapidly. Large sort of international and global scale soil grids, global climate data has been available for decades. And even sort of we see more local scale, sort of continental, the USGS has climate and soil layers available at the US scale. Resolution is still a problem. We sort of like even finer scale for most plant work, but that data is sort of definitely becoming available. Morphological is one of the traditionally sort of fields that has held people back, scoring large numbers of characters, but machine learning is allowing us to process digital specimens with incredible rapidity and even creating more data than we can handle. It's still very much got a learning curve attached to it, but the amount of data and number of species you can process is growing exponentially almost. And so that was sort of phylogenetic data. And traditionally, this was sort of one of the most forward-leading forms of the data we could get. Phylogenies from Open Tree of Life, or our own sequence data from GenBank. But we're sort of finding that if we're looking at entire families, you have to wait for people to contribute to these data sets, and we don't necessarily have all the species or the groups or even all the genera that we need for some of this work. So the slow generation of this data is something that is starting to hold us back. We are working towards solving this, of course. Next generation, high throughput, and the development of markers such as those from Jen Mandel, allowing sort of work across entire groups of species, should start to sort of bring together interchangeable data sets and high throughput studies that we can sort of link together and start to sort of flesh out some of these larger groups. But as it stands, we're still really dealing with a resolution at a sort of a gross scale. The most recent work from Jen has just started to sort of resolve the backbone of the family. This shows the tribes within the family sort of at a global scale, and highlighted the tribes that are majority endemic to North America in yellow there. And so for us, this was what we wanted to sort of to focus on. It gives us 4 sort of quasi-independent lineages, and then a number of less independent lineages within that, in order to test sort of hypotheses of diversification within these groups in North America. So as I said, we have 13 different tribes representing about 4,000 species across North America. Spatial data, we sort of went for the traditional route, of course, to GBIF and IDIG-Bio. We pulled down a little over 3,000 species, and the initial 2 million records was winnowed down to about 500,000 records through cleaning, gives us sort of good coverage of the continents and good coverage of taxa as well. To look at patterns of diversity, richness, and turnover, we aggregated this to 100-kilometer grid cells. And we find that, and unsurprisingly for those in the field, we have high levels of endemism and diversity and richness and turnover, in this case richness, in the west of the continent and the southwest of the US. This is sort of arid, deserty environments, lots of change in elevation, change through time as well. But also this sort of environments that are hot and dry and relatively inhospitable. And sort of areas that we think might be conducive to these sort of extreme elements that might be driving diversification in this group. So we're interested in trying to quantify what is an extreme environment. And that is sort of what is not typical for a plant to live in. It's outside the optimal range of organisms to survive. So sort of a gross way to try and get a handle on this, we decided to try and define the upper and lower bounds of the environmental variables that we would consider useful, sort of pertinent for plant growth. So we found 24 relevant non-correlated variables from climate and soil globally. And then we delimited the top or bottom 5% for each continent and stitched that together on a global scale. So we had a map of where the most extreme end of these elements were. We then layered these different variables on top of each other, and we get a heat map for where we find the most extreme and less extreme areas in the world. Where do we find the most variables are in their upper 95%? And where do we find these sort of co-occurring together? And our hypothesis would be that where we find these sort of highly extreme environments, we would find species diversity decreasing. It should be not conducive to plant diversity. So we tested this using global plant diversity for all plants, all flowering plants, and also for our North American data set for the Compositae. And we found that for North America, for the all flowering plants, we actually found counterintuitively that diversity goes up as the number of extreme classes increases until there's a crash right towards the very end. It's surprising, but we expect to find the same in Compositae. It's our hypothesis, and indeed we do. And it's so strong is this signal from Compositae that we wondered what maybe would happen if we subtracted one from the other. And if you take away the richness and diversity signal from Compositae, we find that it almost entirely removes the signals we find in flowering plants as a whole. And this suggests that Compositae are in fact driving this signal and diversification in extreme environments. So something is going on in this family that they're finding sort of this niche, or this series of niches with extreme environments where they're happy to diversify. But what are the specific environmental variables that are doing this diversification? And sort of knowing where they grow, that sort of southwest area, it's been left relatively undisturbed by glacial cycles, although there have been climate fluctuations. But it's been a sort of a relatively dry, or certainly drying area, where weathering of soils is going to be happening in sort of dry conditions. This means that geochemistry, things like soil salts, start to saturate and increase. So we'd expect to find that over time, species adapt and diversify in these increasingly geochemically rich environments. We'd find a positive correlation between species turnover and geochemistry, and specifically sodium and pH. This is sort of the species pool hypothesis. And if we look at generalized additive models, we can in fact see that for pH, which is the boxes on the left of the two columns, the gray bar indicates the range typically considered optimal for plant growth. That diversity, as we move along the x-axis, increases outside and above this sort of habitable zone. So it looks like, in fact, as pH increases, so does diversity in the tribes of Compositae. We find a similar pattern in sodium. Here you see the dotted line that shows the top 85 to 95 percentile for sodium variables in North America, and there is almost a universal bump in diversity in the Compositae tribes at this value, which is relatively high. So again, it looks like high sodium diversity, high sodium concentrations is correlated with high diversity in the Compositae. And so this supports our hypothesis. Do we find the same response with phylogenetic diversity, however? Would we expect to? So unfortunately, we lack a well-sampled Compositae phylogeny. We also lack a background value for all flowering plants as phylogenetic diversity. But we sort of did an initial pilot to look at the diversity of the Asteriae tribe phylogenetically. And as you can see on the right there, phylogenetic diversity actually very closely maps to normal species richness. So we would expect to find similar patterns for some diversification as well, that they may be tracking these geochemical variables. So we set out to generate a phylogeny for the 14, 13 different tribes in the Compositae in North America. To do this, we went to the Open Tree of Life. We pulled down a phylogeny for those tribes. We included new sequences from GenBank and grafted in some species that were missing in the Tree of Life. We reiterated multiple times, resolving some polytomies, checking misclassifications, adding missing taxa, until we had a phylogeny that we were relatively comfortable with. This was about 1,600 taxa, which seems like a lot of terminals, but it represents about half the data. So we've already had to throw away about half the data we have from our spatial data set. We're still also dealing with polytomies, lack of support values, and taxonomic conflict. So there's a bias towards groups that people are concentrating on, and there's still sort of underlying, there's a traditional taxonomic backbone. So it's still not an optimal data set. We went ahead and used it. We're using tip rate correlation test. I won't go through the details particularly, but we were looking for a correlation between environment and diversification rates in that tree. And again, we had to throw away half the tribes just because we didn't have sufficient phylogenetic resolution in them. So for the 7 remaining tribes, we find that diversification is positively and negatively associated with geochemistry almost exclusively. It certainly seems to have an overwhelming impact on diversification in this group. So this it describes sort of up to 50% or more of the diversification rate within these groups. Which specific variables differs between tribes, suggesting they might be exploiting different variables. But definitely these geochemistry factors are playing a large role. And this is consistent with evolution on these sort of heightened geochemical gradients that sort of persist despite fluctuations in the weather cycles. So I guess sort of the takeaway that we're trying to drive at here is that the spatial environmental data for testing large-scale macroecological questions is certainly maturing. And we are now really starting to see that it's the phylogenetic resources that we're lagging behind. Metaphylogenies are a good starting point, but they do lack some cohesion, and there's still quite a lot of uncertainty. However, we do have the resources going forward to work on this. Things like the bait set should allow the community, if we can come together, to sort of work together and collaborate and generate trials that are intermittable and that we can use to complement each other to sort of tackle these large phylogenetic questions. That will then flow through into being able to take on these large ecological questions. And so groups such as the International Compositae Alliance, TICA, which is sort of regenerating again, should allow us to sort of start to work together as a community to tackle these questions. And on that note, I'm starting a new postdoc in a month's time at Yale in the YETS lab at the Center for Biodiversity and Global Change. And there I'll be sort of taking these methods and what I've been doing at the North American scale and looking at a global Compositae and the response to the environment. And so again, I'll be sort of looking for experts and the taxonomy community, Compositae community, for expert assistance with taxonomy and curation. So I'd love if anybody who's interested to reach out, I'll be sort of reaching out to the community as well sometime in the future. And we hope we can really start to work on some of these questions at a grand scale. I've got many people to thank. All these people have helped in various ways, particularly Jennifer Mandel, her support in the last year. But I think we all sort of have a soft spot. Vicky Funk, who brought together so many people who work not only in Compositae, but plant systematics in general. She's been a wonderful mentor for me. And I hope that in answering these questions, Vicky was always a great advocate of broad scale questions, that we'll be able to continue to carry her legacy forward. And I think we will be able to work towards that, and we'll continue to push her work. I'll leave you with the references. Thank you very much for taking your time, and I look forward to taking questions from you now or sometime in the future. Thank you very much.